12.4 is still dealing with probability, as you saw in the quiz today, or yesterday. So we're going to keep going into probability. It's looking at probability distributions, so looking at how various, what the distribution looks like, and assigning probabilities that way. Okay, so quick model here. Mr. and Mrs. Mason have 3 children. Assume the probability of having a baby girl is 0.5, as in you have a, what, 50-50 chance of getting a boy or a girl, right? And the probability of having a baby boy is also 0.5. Now, you have a model A and a model B here. Question A is, which model represents the situation correctly? Model A or model B?
Model A.
Why? Because you had to throw something out there, right? Other thoughts?
Let's B model because it has boys and girls. It's not just.
Okay. And what's this one showing? This model A is showing it's equally likely to have no girls, 1 girl, 2 girl, 3 girl. Is it equally likely to have those various combinations? Probably not. What's happening here? The first choice is you're going to have either a boy or a girl. If you get a girl, what could you have next? Girl or boy. Okay, if you had a boy first, what could you have next? Girl or boy. And then with each of these, we have another option, yes? License violation. I don't even want to know. Okay, so model A is the correct answer. Excuse me, model A is not the one that represents it correctly. Model B. Sorry, I'm a little flustered at this point. Okay, whether your first child is a boy or a girl does not affect your next child, whether it's a boy or a girl, right? So each event is an independent event, and they're not all going to be equal. Okay, so which model? Model B. Each event is independent. And I'm going to say not all options are equal as shown in A. Okay. With that, what is the probability that Mr. and Mrs. Mason have 3 girls? So obviously we're looking at model B here, yes? They've got all tallied up for us over at the right. What's the probability we have 3 girls? How many times does 3 girls happen over here? Once. Out of how many different possibilities? Okay. 8 possibilities there, yes? So probability that they have 3 girls is 1 out of 8, which could be written as a decimal. 0.125, which could be written as a percent. 12.5%. Yes? Okay, all equivalent there. Compare the probability that the Masons' first child was a boy and they had 2 girls to probability that their first 2 children were girls and then they had a boy. Does the order affect the probabilities? So I feel like I need to read that again here. Probability that the Masons, what was it? First child was a boy and then they had 2 girls. So I'm going to call that BGG, as in boy, girl, girl. To the probability that their first 2 children were girls, and then they had a boy. So girl, girl, boy. Okay. So, how many times did boy, girl, girl happen out of these 8 options? What do we have here? Boy, girl, girl. Does it happen any other times? No, because these start with girls, don't they? So there's 1. 1 out of how many? 1 out of 8. What about girl, boy, boy? What do we see here? Girl, boy, boy? How many times does that happen? Which is it? Because I just did the opposite of what I wrote, so regardless, I'm wrong somewhere.
Children were girls.
Okay, so it is supposed to be girl, girl, boy, but I did not just do that, did I? Okay, so again, somewhere I'm wrong. So try this again. Girl, girl, boy. How many? That's happening once. Did it happen any other times? No. Goodness. Trying to hurry and be quick and not succeeding. Take a breath here. Now, does the order affect the probabilities? No, in both cases, it's 2 girls and a boy, yes? Does that order affect? No. Okay. And so, order is not going to make a difference. Each probability is still 1/2. So, how do I want to... So, order does not make a difference. And I'm going to say each probability is 1/2, and I'm going to talk about that. Now, when I talk about 1/2, I said 1/2 without showing where I'm talking about 1/2. When we talk about having a kid, what's the probability of having a boy first? 50-50, right? 1 out of 2, 1/2. What's the probability of having a girl second? 50-50, right? 1/2. What's the probability of having a girl third? 50-50, 1/2. Same going to be true down here? Yeah. And so either way we look at it, it's going to be a 1/2 times 1/2 times 1/2, which guess what that equals? 1 times 1 times 1 over 2 times 2 times 2, and there you have that 1/8. Okay, so the tree diagram here is really helpful. It gives us the visual to look at. However, we can also think 1/2 times 1/2 times 1/2, which we've done somewhat already this lesson, or this chapter. Okay, so probability distributions, being able to look at all the possibilities, being able to look at possible outcomes, and putting those probabilities together. Now, you have a few definitions next. Sample space. This is vocabulary that you always see with probability. Sample space being all the different possible outcomes. So sample space is a set of all possible outcomes of a situation or experiment. So sample space. So what we had back there, the girl, 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 boy, boy, all those different possibilities, that was our sample space. There's going to be 8 different possibilities. Then the other vocabulary, a probability distribution for an experiment is a function that assigns a probability to each outcome of a sample space for the experiment. Okay, so it's distributing the probability. It's assigning a probability to each item. We'll kind of dig into it a little bit here with this first one. I'd ask us to develop a theoretical probability distribution. So we're going to look at the probability of all the possibilities. So Tio and Henry are running for president of the student council. You will select a campaign button at random from the box containing 3 Tio buttons and 3 Henry buttons. you'll record the number of TO buttons that you get. What is the theoretical probability distribution for the sample space? And then they have the sample space listed as 0, 1. Okay. 0, 1, that's two options here. Now, what are we recording? The number of TO buttons you get, right? So probability 0 is going to be the idea that you get no TO buttons. Probability of 1 is that you do get a TO button. Okay, so let me write that out first, and then we'll go through. So you have to understand, you know, when they're saying 0 and 1, they're indicating that the probability of not getting a TO button, so I'm going to put no TO button, is what we're talking about with probability of 0. We're going to talk about that. And the probability of getting a TO button is P of 1. Okay, so go back and look at what was the question in place. Here the question in place is you're going to record how many TO buttons you get, right? We don't care how many Henry buttons we get. How many TO buttons do we get? So with TO buttons, you don't get a TO button, P of 0. You do get a TO button, P of 1. Does that make a little bit of sense of how I understood that? Okay. Now, there are 3 TO buttons and 3 Henry buttons in this box, right? What is the probability that I do not get a TO button? 1/2? Because why? 3 and 3. How many, so think of it, entire option, all options on bottom. How many options are there? How many buttons am I pulling from? There's 6, yes? Probably of not getting a TO button. How many buttons are not TO buttons? 3. So 3, 6, which of course is 1/2. Okay? What's the probability of 1? So probability of 1, that is probability of getting a TO button. What's the probability of getting a TO button?
3, 6, 6.
There are 6 buttons. 3 of them are TO, so 3/6, which is 1/2. Okay? So that right there, the fact that P of 0 is 1/2 and P of 1 is 1/2, that is our probability distribution. It's distributing the probability, it's showing the distribution of the probabilities to our different options. Okay? Now, B, we're going to change it up a little bit. Now you plan to select a button at random, put it back in the box, and then select another button at random. Okay? You'll record the total number of times you get a TO button in the experiment. Define the theoretical probability distribution for the sample space 0, 1, 2. How does this probability distribution differ from the distribution in part A? Now, as we look at this one, 0, 1, 2. What's 0, 1, 2 going to represent? 0 is going to be getting,
2 Henry buttons.
okay, or I'm going to call it 0, no TO buttons, but I agree, it would be getting 2 Henry. What's 1 going to represent?
1 of each.
Okay, ends up being 1 of each, technically 1 TO button, and 2 is going to represent getting 2 TO buttons. Are we seeing that? Now, in order to represent that, it's a little bit more this time because we have to look at, we're going to draw one, we're going to put it back in the box, and then we're going to draw a second one, yes? Not saying you need this, but I'm going to think tree diagram real quick. On my first draw, what could I possibly get? Okay. I could get TO or Henry. Okay. If I draw the TO button the first time, what could I get the second time? I put it back so I could get TO or Henry, yes? What if I got a Henry button the first time? What could I get the second time? TO or Henry. Okay, that's my 2 draws. Now, If it helps, you can write these possibilities out. One combination is getting what? TO. What's this next possibility? Getting TO, then Henry. Here we could get Henry, then TO. Here we could get Henry, then Henry. Now maybe you don't need that visualization, but I need it to teach if nothing else. Okay? We're being asked for our probability distribution. So probability of 0, probability of 1, probability of 2. And again, what is this all in regards to? TO. So what's the probability of 0? What'd you say? The Henry, which is how many choices? That's one choice out of how many? 4. So 1/4. Okay? I just put a 0 there just to indicate that that's where we took it. What's the probability of 1? It could be T.O. Henry, or it could be Henry T.O. That's how many choices? 2 out of 4, which is 1/2. Probability of 2. There's one option of getting TO, right? So 1 out of 4. Okay, so our probability distribution is this right here. Okay, that's our probability distribution for that sample space. Now, the question is, how does this probability distribution differ from the distribution in part A? What do you notice in part A? They're the same. What do you notice in part B? They're not the same. They're different. So I'm going to use the words, part A was uniform, as in all the probabilities were the same. Okay, so our probability was evenly distributed amongst all options. Whereas part B is not uniform. Okay, not all the options were evenly distributed. Okay? And keep in mind, folks, all these probabilities, I don't know if you're noticing, they add to 1. Okay, they're all going to total 1. Now, I'm going to skip the example at the top of the next page that talks about marbles, because, man, I'm going to be pushing on time anyway I do this, okay? I will put marbles in a video, so you can go back and get those notes and get another idea of how to do it, okay? So I'm going to skip this screen. We're going to talk about this one. Developing an experimental probability distribution, okay? So, slightly different situation here. A cell phone company surveyed 500 households about the number of smartphones they have that are in use. Would you recommend that the company concentrate on selling data plans for individuals or plans for families with 3 or more smartphones? Okay. So, with this in mind, a couple of things to look at. 1, finding the experimental probability distribution by finding each relative frequency. Information in this chart: number of smartphones per household and frequency. Do you remember what frequency is? The frequency of something is going to be how often it happens, how often it occurs. So this is saying number of smartphones per household, 0. 0 smartphones happens 10 times throughout this, 500 households. There's 66 households that have 1 smartphone, right? All the way up to there's 44 households that have 6 or more smartphones. Okay? Now, in order to look at the probability of each of these, we have to look at what I'm going to call the relative frequency. And I don't have a line here on this chart, so we're going to make our own. Relative frequency is what's going to lead us to the probability. I just said there's 10 households that have no smartphones, right? 10 out of how many? 500. So the relative frequency here is 10 out of 500. You're going to want calculators because we're going to change this. Decimals or percents? I have both. We're going to end up talking percents to answer this question. What is 10 out of 500? 0.02, which if we change this to a percent is 2%, yes? Okay. What about one smartphone? Happens 66 times. 66 out of how many? 66 out of 500? 66 out of 500, according to the calculator, is 0.132, or in other words, 13.2. Well, I just have 13% on my paper, so I must have rounded to a whole number. So 13%. Okay, two smartphones. Happens 120 times out of 500. As a decimal, that is 0.24 or 24%. Three phones, the most typical, right? 144 households out of 500. As a decimal, 0.288. To a whole percent as a whole number, I have as 29%. Four smartphones. Happens 79 out of 500 times. As a decimal, 0.158, which rounds to 16%. Five smartphones. 37 out of 500. I have down 0.074, which is 7%. And finally, 44 smartphones out of 500. That's for 6 or more members of the household, or 6 or more in a household. That is 0.088, which is approximately 9%. Okay, so being able to find your relative frequency, taking each of those frequencies, looking at total what they're coming out of, and we were able to change those to percents. Okay, so this is saying what? The highest, 29, is at 20.9%. So three smartphones per household is happening 29% of the time. And that's the highest percent there. Now, that's part A. Just finding each probability using the frequency. 2, we're being asked to graph it. So we talk about graph. Along the left is the probability. We're thinking like bar graph here, folks. Okay, nothing fancy. So along the bottom, what are my different categories? We're going to have 0, 1, 2, 3, 4, 5. And I'm just going to put 6 plus for my 6 or more. And what is that? That is the number of smartphones per household. Okay, so obviously these bars are going to be kind of estimates here. Zero phones was approximately what? 2%. Okay, I'm just doing bar graphs, so my bars aren't going to be touching. One phone was approximately 13%. Two phones was approximately 24%. Three phones, approximately 29%. And mine's not perfect by any means, but we have the data to support it. Four, 16%. Five is at 7%. And six or more is at 9%. Okay. That gives you a little idea of the probability distribution, okay? I don't know off the top of my head. I haven't added these up. But these percentages should add to be around 100%. I'm going to say around 100% because we did some rounding, didn't we? So could they be slightly off one way or the other? Possibly. But with that in mind, this is showing how the probability is just distributed. Can't say that word because I'm trying to hurry. Now, what was the original question? Because there was a question here. Would you recommend that the company concentrate on selling data plans for individuals or plans for families with 3 or more smartphones? How can we answer that question using this information to support it?
With the number of household smartphones, and then everything to the right would be what they want to sell, because there's more
Okay.
phones per house.
Okay. So they talk about plans for families with 3 or more. So 3 or more would be, I guess, these right 4 pieces, right? And then, so that means selling data plans for individuals is going to be more the left, the 0, 1, 2. So if we look at this, and how I have it on my paper is, if we look at the groups that are less than 3, and if we look at the groups that are 3 or more. Okay, look at those amounts. Less than 3 is what? 2%, 13%, and 24%. Well, 2 plus 13 plus 24 is what? Approximately 39%. As compared to families with 3 or more. So 3 or more, what are we looking at here? 29, 16, right there. I think I already know my answer. But still plus 7 and plus 9. 61. Okay. With that in mind, what's my data supporting? Data is supporting that where's your best marketing going to be? Those family plans. Okay, so family plans, since 61% of the households have 3 or more smartphones. So, family plans, since 61% of households have 3 or more smartphones. Okay? Okay. The top of the next page is another similar problem. Okay? Talking about the drama club, looking at experimental distribution, looking at a graph, all that. I'm going to skip that one. I'm going to go down and talk about binomial experiments. Because even at that, I don't know. How did I get through these notes in 2 days in the past? Okay, so probably the last topic of the day, binomial experiments. Okay, so you have some key pieces here about what a binomial experiment is. Okay, there's certain pieces it has to meet. Binomial experiment is an experiment that consists of a fixed number of trials with the following features. Each trial has two possible outcomes, one of which is denoted as a success. So the idea that there's probably whatever you're looking for, the success, and that you can term everything else as the rest, essentially. The results of the trials are independent events, so one result does not have anything to do with the other. And the probability of success is the same for every trial. So basically we're looking for uniform results as opposed to not uniform results. So those are your three pieces here that are important in deciding if something is a binomial experiment. So look at A. Is this experiment a binomial experiment? This spinner is spun 3 times. Assume that the spinner is equally likely to stop in any of the sections. Success is landing on a section marked go forward 2 spaces. So, first thing, we need to talk about, are there 2 possible outcomes? What would be deemed success? What are we trying to do here? Go forward 2 spaces. So success is landing on go forward 2 spaces. And then what's the other alternative? Not landing on go forward 2 spaces. Does that make sense there? Okay, so when we talk about 2 possible outcomes, one outcome is landing on go forward 2 spaces, or the other option is not landing on those spaces. Okay? So we can lump it into 2 options. Landing on what they were looking for, go forward 2 spaces, or landing on something else. Whether there's 1 something else or 5 something else's. So we can consider this as 2 possible outcomes. Like we can check that box, so to speak. The next question, are the results independent? Okay, are the results independent? What do you think?
Yeah, because even if you land on before one time, the next time it's still.
Yeah. Does one spin of the spinner affect the next spin of the spinner? No. What happens the first time does not affect the outcome of the second time. So that means that these are independent events. One spin does not affect the next, is what I'm going to write. One spin does not affect the next. Okay, so we can check the box that they are independent of each other. Now, probability of success is the same for every trial. So when we talk about the probability of success, what is the success here? That's probability of landing on go forward 2, right? What's the probability of landing on go forward 2? One-fourth, is that right? 2/8, 1/4. Now, is it going to be the same the next time you spin the spinner?
Yes.
Yes. Kind of goes along with, is it independent? Okay. And so it's going to be 1/4 each time. So I can check that box. Does this meet all 3 criteria for a binomial experiment? Yes, it does. And so for this one, I can say, yes, it is a binomial experiment. Okay? Okay. Do we have time to talk about B? Because you know what B is going to be, right? B is going to be, if this is a binomial experiment, B is not a binomial experiment because that's how I often teach. Now, what's the catch on B? Yeah, okay. So here, class of 23 students, 7 students completed the term project. 2 students selected at random have to give presentations. Success is that the student has completed the term project. What's the probability, I'm going to jump right into this, that the first student has completed the term project? There are how many options that have completed? 7 out of 23. Now, what's the probability that the second person has completed the term project? We're no longer picking from 23. We now only have 22 options, and we only have 6 options. You can do the math. Those aren't the same. Okay? Your calculator will tell you. And so right there, because these guys are not equal, okay, that's supposed to be a not equal sign, this is not a binomial experiment, okay? These are, we could say, not independent and not equal probabilities. So for that reason, it's not a binomial experiment. Now, what I did not write up here, were there 2 outcomes on this one? There were. I skipped over that in my hurry. You would always want to check that first. Okay, now, tomorrow, there will be a video later tonight, but it might be late tonight, because it might be after softball before I get it recorded. So, later tonight, there will be a video to finish notes, okay? Savas will be available. Those are your goals tomorrow during class, okay? You might bring earbuds, listen to the notes, do Savas. Not to be able to get all done one period, so plan on doing something outside of class. Behave tomorrow.